before. And so we can go through this today and I guess Wednesday. This is a good, and maybe use this example as a vehicle if you want to go through the whole course. Okay. So we can write the equations, look at the coupling, check contractivity, for example. Okay, then see what kind of staggered approaches we could make out of this. Okay, I could have kept this for the exam actually, but okay. This would have been a good exam example. But here, okay, we're going to take the time and going to have you maybe. I'm not going to do it in exam mode. Okay, we're going to take more time and go discuss more things. But really, the idea is to go through the different steps. Okay. So. Maybe first question is, what do you remember from power elasticity? What do you know about power elasticity? You had a course on power elasticity, right?
Yeah. There was the solid phase and then the fluid phase with no strength.
Okay, so there is a, let's see, okay, so we have our, maybe I should do it this way. Okay, so I've got my continuum mechanics problem as usual. And okay, if I zoom at what I consider as a material point, if you want, okay. Okay, I've got the skeleton and the force, okay? Okay, and you see this as a homogeneous continuum from the continuum mechanics point of view. Okay, so, and okay, so what you have. Okay, so you're going to look at a simple case, okay, because this can be quite complicated, but we're going to take a case where it's saturated with an incompressible fluid, okay. Okay. And then the coupling comes from the, okay, so if you take one of the pores here, this is not very clear, but okay. We have different things. We have the fluid in the pore, there's some pressure, okay, we do P. P is the, in this case, is the fluid pressure, it's not the pressure in the solid. Okay. We can also characterize this by the porosity. Okay, which is the ratio of the porous volume with the total volume. Okay. And of course, okay, so this we can call this an RV, a representative volume element, if you want. Okay, so this can deform. So we're going to consider that this is, okay, this is one hypothesis which is not. It's going to simplify things. The fluid is incompressible, but the change of so the density of the fluid will not change. Okay, this is the idea. But the volume of the pores can change because if I stretch my RVE here, I can change the volume of the pores. So the skeleton is also elastic, so it can the pores can grow or decrease, and that's the way the porosity change, and this is going to change the total content of fluid in the RV. Okay, and of course does not show here because it's two decays, but the pores are connected. Okay, so the fluid actually, because it's incompressible, so if you change the volume, the amount of fluid is going to change because the volume is diminishing, for example. The fluid is able to go out, because otherwise, if you had an incompressible fluid and non-connected porosity, this would be like rigid inclusions in the matrix, so this would not make a lot of sense. But anyway, we're going to make a simplified version of it. Okay. Okay, so if we want to describe the problem, so you can describe it in terms of different fields. Of course, okay, you have the mechanical field. Okay, you can have a strain on the RVE here, some stress and everything. So the balance equations we have. We start with this. Well, we can write them. They are quite classical. Okay. Of course, we have the mechanical balance. Okay. If I write it in statics. Okay. And the continuum level, this remains true. Okay. And okay, so what about the other one? So if I look at conservation of mass, I can still write it in the classical way. Well, I mean, exactly the same way as we have done before. Okay, with the concentration and the flux, just as before. Okay, so now here we can try to connect this with our description here. Okay, so we need to have the differences. Okay, so the concentration. Can describe it, there are different ways, different notations which can be considered. I'm not sure what was, well, I have an idea of what you have seen in the other course because he gave me some slides, but there are different ways to do this depending on what subfield you are considering, I guess. But there is one way to, this concentration can be defined in different ways. I mean, you can use different units. Okay. So one way is to use people who are more into chemistry. We will tend to work with a molar concentration. Okay. Moles per unit volume. Okay. Moles is not a very thing that mechanicians do, but chemists, that's what they think. Okay. So in this case, I'm going to be able to define the concentration. It's going to be into the porosity divided by this thing is the molar volume. So volume of 1 mole of the fluid. Okay. to remember what is a mole is the Avogadro number of molecules of the same. Okay, so this is okay. This is the way chemists typically work. So this polar elasticity can be used in very many different fields. Okay, of course, it comes from civil engineering, soil mechanics, and everything. But people working in biomechanics, for example, will use this as well. I mean, so if you take a bone, it's a porous medium. If you look at a hydrogel, it's also okay. So in this case, the units. Okay, in this case, it's going to be. So if you look at the, so it's going to be moles per volume, the total volume. Okay, how many moles are there in 1 cubic meter of porous, saturated porous medium? Okay, so. And again, you can check that, of course, that in this case the C. So phi is the volume of the pore divided by the total volume, and the molar volume is going to be so the number of moles. So the volume for number of moles. So it can be number of moles that there are in the pores divided by the volume of the pore. It's the volume of the pores divided by the number of moles in the pores. Okay, and so in the end you get the molar concentration, the number of moles divided by the total volume. So this N, okay, maybe I can is the number of moles of the fluid of the in the pores, the pore volume. So the molar volume is a volume per moles. So the omega F is the volume of pores divided by the number of moles in these pores. Okay? Well, but this is okay. This is one way to do it, and I don't think this is the way this was presented in the previous course. I don't know. You tell me. No. So okay. So in mechanics, we will prefer to work with the mass concentration. Okay. So you're going to say that the concentration is going to be density of the fluid times the porosity. Okay. Okay, and since we assume that it's incompressible, this is a constant. Of course, we could make it compressible, then it's become more complicated. But, okay. So I would say, of course, in this case, the concentration is, and of course, I mean, there is for a given species, there is each mole is a certain weight. And you can connect the two, of course, pretty easily, but, okay. It's at least in the incompressible case. So in the incompressible case, if you work with one or the other, it's just the same. In the compressible case, it's going to be different because the number of moles is going to be constant, but the density can change. Okay, so we need the extra equations and everything. But, and of course, I mean, this means that the flux also has to be defined in terms of it's a massive flux or a molar flux. How many moles per second per square meters, or how many kilograms per second per square meters. You need to have a dimension for this. This means that in this case, for example, this would be mole per second. Okay, we'd have to define the flux in a consistent units. Okay, and in this case, it's going to be a mass flux. Okay, so this is just to make the connection between our quantities here, or the main quantities. So we want to describe things in terms of the porosity, which is one of the essential quantities used in the power mechanics. This just shows you how you connect it to concentration. And okay, these equations we have treated them already. They look very much familiar normally. When you write this, I mean, okay, this applies the way that the transport, and if you want, is it by diffusion or by actual transport? I mean, but these are two different cases, of course, but you can in the end, I mean, the balance equation is the same. Okay, so if you, just to say that, okay, this is a simple case because if you are now looking at cases, okay, if you look at aging of concrete, for example, you will look at the concrete with water, and in the water you have some ions, sodium ions, or it depends on the salt on the seaside. And then you can have the diffusion of the salt in the water, and the water itself is moving. So this can become a bit complicated. Okay, we won't go that far. Okay. Oops. Okay, so the question now is. We don't have enough to solve the problem now. Okay, we have this. We have these equations, but we need to connect the stress to the strain, the porosity, the pressure, the flux. To connect all these together. Okay. Okay, yeah. You can also, okay, if you want to do the last connection with the what you have seen, I guess, in the course. Okay, this flux. Okay, if I work in this version, okay. So the mass flux is going to be this is an equation you must have seen in course. So I'm going to, well, I mean the people in power mechanics at least, they would introduce the fluid velocity. Of course, you have the solid is moving, I mean the skeleton is moving as well. So these are absolute velocities in the reference frame. So of course the flux is the relative motion of the fluid with respect to the solid. Okay. And okay, so this is the velocity in meters per second, and okay, so this is the concentration, the mass concentration. Okay, this is just our C. Okay. Now, okay, we won't go too much into. I'll do all the work with the flux, but if you want to work with the velocity, okay. If you want to linearize things, okay, can also be. Want to linearize can be if this is your unknown, if you want to write the things in terms of the okay, you may want to approximate this by considering that there are few little variations of porosity, okay. If you want to have linear equations in the end, in terms of you can do this. But okay, what we'll do, we'll work with the flux directly. It's easy. Okay, but okay, this equation we don't going to really use it, but since it's in the course, I wanted to make the connection. Okay, I'm going to work with the flux directly. For what we want to do, it's enough, I think. Okay, so we want to connect all these things together. All right. Okay, let's see. I can leave this for the moment. Okay, you can take me. Okay, where is this tool? Okay, so it's always the same thing. We need to have a complete set of equations. We need to introduce constitutive assumptions. So again, what do you remember from the? So we need to write relation between the stress, so the porosity, or the concentration if you want, in this case. But we need to work with porosity. Okay, we also have the pore pressure, we have the flux, all this together. Okay, so do you remember anything?
It's been a long holiday, sir.
Yeah, no, I know. I'm just trying to.
The stress is the Hooke's tensor times the strain plus the Beal modulus something?
No, in this case we don't have plasticity, so we're going to, okay, there is a contribution to the stress which is clearly, okay, so this will be elasticity, okay, so we could assume that the skeleton is elastic. So clearly if we apply stress or strain, I mean, if we apply stress, the skeleton is going to deform, okay, but we have more than that. Okay, so there are different ways to introduce this, okay, so now there is another way to generate stress in the skeleton. Okay.
Oh, it's the pressure.
Pressure. Okay. If I put pressure,
Identity.
okay, this is going to something is going to happen. So. Okay, the way it's usually, okay, if I put pressure and I assume a linear theory, the amount of stress is going to be proportional to the pressure I put in the pores. And there is this B tensor, which is going to be describing the quantity. So usually it's a spherical quantity, so it's just a scalar times identity. Okay. You remember how it's called, this one? This B?
Biotensor?
Yes. So the guy who invented poroelasticity or something, the modern poroelasticity is Bio. Okay. So, do you remember the first name of this guy? The strange first name is in a way because it's a mixed French-American name. It's Maurice Anthony Bio. Yeah, he was born in Belgium and this most of his career in the US. Okay, and of course this is okay. At least for isotropic cases, it's the elasticity force of the tensor. Okay, so this B depends on the morphology of the porosity, the material. It depends also on the bulk modulus of the skeleton, of course. This is something you can get experimentally. Okay. Because if we look at it, we can look at this a bit more detail afterwards, but basically it means if I have one way to see this is that either you block the strain, you inject fluid to increase the pressure, and you measure the stress, like if you have a way to measure the stress in the material. I mean, basically if you confine this, you inject water, it's going to push on your
Boundary?
cell, on the boundary, yeah. But if you are able to measure the stress applied by the material on the boundary, you can get the stress, and you see that, of course, if there is no strain, and the B is a spherical tensor, the material is in hydrostatic pressure, and the ratio between the pressure you put in the fluid and the pressure you get for the bulk is going to be your coefficient. Tensor, in general it's a tensor, but okay, typically it's taken as a scalar times a unit tensor. Okay, all right. Okay. What else can we write? There are three equations we need. Okay. Remember anything else? So you can also connect so there are different ways to write this, but you can try to connect if you apply some pressure, okay, you're going to generate stress in the skeleton, but something else is going to happen.
Will there be displacement?
Okay, no, but try to think about this little cell, okay? So we have an elastic skeleton, and I'm injecting and pushing by increasing the pressure in the pores. Okay, I'm generating stress in the skeleton, okay, which is generates stress, an average stress on the bulk, the homogenized bulk, okay, which is what we have here. Okay. What else? What else is happening? Try to think. Guess something there.
We have pressure in voids, so changing the volume of the void.
Yes, exactly. So the porosity is going to change. Okay, the material here is elastic, so if you push on the pores, I mean, they're going to deform, to increase. Okay, so we can write a connection, the relation between the porosity and the pressure. Okay, and so so this can be written in different ways, but so if I take it in the way that it's done in the so the variation of the porosity comes from two parts. It's into two things. Okay. So it's going to be okay here. Let me write it like this for the moment. It is going to be linked to pressure. If I apply pressure, the porosity is going to increase. And also, another way to increase the porosity is to deform the skeleton. Okay. Okay, and it turns out that so if you have macroscopic strain, the porosity is going to increase. Okay. Okay, and this is the same. This is the same phenomenon as here. Okay. It's just if you deform the skeleton, so there is a stress associated to it. Okay. But then this will deform the pores as well. Okay. Or in another way, how does the pressure in the pores generate stress in the skeleton? Is by deforming the pores and increasing the pores and deforming the skeleton, which is generating the stress. So that's not completely a surprise that it's the same B in both sides. Okay. And the N is another BO quantity on this one. So okay. Okay, so just with respect to the equations that you can find normally in the Professor Scher's course, I mean, he's using a P0, an initial pressure, which I set to 0 here. It's simpler. You could consider that there is an initial pressure, and that but then the stress is always. There is no absolute zero for stress. I mean, it's just the atmospheric pressure exerts some pressure, some stress on everything. But you treat this as 0 because it's your reference state. Okay. So here, that's why I'm setting the P0 as 0. It's just a matter of reference.
So B as a biotensor in the first constitutive equation, and N is the modulus in the second?
Okay, so that's why there are two quantities which are different.
Mm-hmm.
They are linked, of course. I mean, they can both be obtained from the properties of this RVE, but they are two different objects. One is in general is a tensor,
Mm-hmm.
second order tensor. So this is the into the stress which is generated when you apply pressure in the pores. Okay, or if you want, you can see it in different ways. If you deform globally the RVE without changing the pressure, okay, the pore pressure, so just the fluid doesn't see any pressure changes. It just has more space, so it's going to occupy more space. So there will be more fluid because it's incompressible in this case. I mean, it means that you are putting the maybe I've prepared this also, but you plunge your material in a bath of fluid, which is at a given pressure, then you deform it. So it's going to suck some fluid if you expand it. Okay. The question is, when I deform it by epsilon, how much volume change is there in the pores? Okay. So this is just linked to the morphology of the pores, porosity, the elasticity of the material and things like this. Okay. In the simplest case, if you just had one sphere in the middle of another sphere and everything is homogeneous, homothetic, the B would have probably a very simple expression, but in practice it's a little bit more complicated than that. But okay. And this one is a different one. It's just so if I block the strain, again, if I block the strain, I set the strain to 0. Okay, I start from the reference configuration. I set the strain to 0, so this is not there, this is not there. So you can measure the two. You could technically, experimentally measure the two quantities separately. So here, you apply the pressure in the pores, and you check how it translates in terms of pressure in the bulk. Okay, so this gives you the B, and then you apply pressure in the pores, and you maybe you do some tomography or something like this, and you try to measure the porosity, measure the volume of the pores before and after. You look at the change of porosity, and you get this N from there. Okay.
But B double whatever is still the biotensor in the second equation.
Yeah,
You
yes,
just have
the
the
same.
biotensor
It's the
in
same.
bio.
This
Just
is
making sure. That's fine.
these are the same quantities. Yes.
Okay, it's a dumb question. It's dumb.
Okay, so we still miss one question. Any reminiscence of something? Yeah, exactly. So we need to connect the flux and actually the pressure gradient. Okay, what is driving the exchange of fluid between one cell and the next, one elementary cell and the neighbor one. Okay, and it's the gradient of pressure between the two. Okay. Okay, so so we can write that at least I will write it in this way in terms of mass flux. Okay, we say that the mass flux is proportional to the gradient of pressure. Okay, and okay, if I try to use the same notations as so we have a network of pores, okay, connected pores. And if there is a gradient of pressure, it is going to push the fluid from one side to the other. Okay, and we say that the flux is proportional to the gradient of. Okay, and if I reuse the notations that were in the Research course, the coefficient I could write it D or whatever, and just some kind of permeability tensor, okay, somehow. But here it's written in terms of K and the viscosity of the fluid. Okay, but okay, this is just a coefficient if you want. Can always. Okay, and this is indeed, this is Darcy's law. Okay. And if you want to write it in the real the original Darcy version, I guess, which is written in terms of the velocities, that's why I linearize it so that this is a linear relation. Otherwise, it becomes a bit more complicated. But this can be handled, of course. The general case can be handled. But I lose I lose the linearity in this if I write it in terms of velocities. But I don't care here because I'm going to write this in terms of the flux directly. And I put the flux directly here. These things can make a difference when you start to go away from the small perturbations theory. Okay, if you want soils, they deform. If you look at sand, I mean, it's not small strands. Okay, you have to define different types of porosities. You have a Lagrangian porosity, you have an Arrhenian porosity. Because okay, this is the. For example, if you look at this is a change of pore volume divided by a reference volume. What do you take as the reference volume? The undeformed configuration volume or the total volume of the deformed configuration? So you can have Lagrangian or Arrhenian porosities. And this starts to make things much more complicated. But okay. In this case, we are in the linear case, so we consider that this is I could put a 0 here, it's the initial volume. I don't worry about the difference between the Lagrangian and the Arrhenian. Okay. So we could reformulate this in a different way. In terms of the framework of generalized standard materials, you know, the framework where we define potentials from which we derive the constitutive equations. Okay, which allows to do variational formulations and everything behind. So this is interesting. It allows you to do thermodynamics, also consider energy conservation, verify dissipation, and everything like this. Okay. So if I look at the this framework, I can define, okay, so I can write, it's also interesting because it's going to show you that you can write in different ways, okay? I can decide that my primary unknown fields are displacement, typically this will change. Then, okay, do I work with porosity or with pressure? I can decide both, okay? So, we can start with the so we can start working with displacement and pressure or strain. So we're going to define an energy, the energy density. Okay, so this is the free energy per unit volume of this RVE, okay? This function of the state of strain, and also the current porosity, okay? So these are, yeah, I could spend a lot of time deriving this, but I'm going to, this can be constructed actually by using these, in the end I will want to obtain these relations by directly from this. Okay, so if I consider this one, and actually, okay, this is so this is the classical elastic density, okay, and I need to put an extra term accounting for the the fluid part in the pores, okay. Again, this I'm just giving you the results as it is. Could derive it in actually maybe the simplest way to derive it is the other way, but okay, we'll see in a moment. But okay, let's assume that I write it in the following way, okay. Okay. So it's always the same thing, okay? The same structure, remember in the thermomechanical case, or in the diffusion mechanics case. The energy density, since we have simple models, what we have quadratic terms. Okay, here if I developed, well, we can do it after. You can define two elasticity models, two elasticity tensors actually from here. But there's a quadratic term here, there's a quadratic contribution in epsilon also coming from here. There's a quadratic contribution in phi, or phi minus phi 0, the change of porosity, and there is a bilinear term which is describing the coupling. Okay, and you see that B and N are describing the coupling. There's actually B which is describing the coupling mostly, but because you see that B is always, P is something to pores, this is into the skeleton, let's say. And here, these pores, this is the skeleton. B is really the cross, the terms which there's a connection, and N is linking pore related quantities through the skeleton, of course, but anyway, this is the, so let's just, we can say a few more things about this, but before that, if we have this, then I can rewrite the Kostic equations in a different way, okay? So I'm going to reuse this space here, okay? Just to show you that in this case I postulate, well, I wrote the Kostic equations individually. Now the idea of this general standard materials approach is that I'm going to postulate two potentials, two functions, a W and then a phi. Okay, we can directly write this. So the other one is the dissipation function. Okay, and okay, we can write it in different ways, but we can write it in this way. It's a quadratic function. Okay, so if you go back to the thermoelasticity case, the structure is exactly the same. The mathematical structure is exactly the same. If you think about it. If you remember, now if you replace pressure by temperature, this will be exactly, okay, you have this almost similar equation for the thermoelastic case. If you remember, in the thermoelastic case, the stress, there was an elastic part and a thermal part. This was the variation of temperature, okay, so it's P, okay. I could write P minus P0 if you want, but the theta, the change of temperature, which is the equivalent of P, and I wrote it M as the tensor, second order tensor, small m, lowercase m, okay. And then this would be something like entropy, connected to the temperature through a heat capacity. This would be N. And the contribution of the strain to entropy. Okay. So it's interesting to see these parallels, because this means that we are going to be able to do all the analysis that we've done for thermoelasticity. It can be reproduced here for this case as well. That's what we'll do after. We can need to write the equations, but okay, we can, for example, check the contractivity, which is allowing us to look at the different algorithms we can use to solve the equations after, monolithic or staggered. Okay. Once you have understood the connection, and if you know well your thermoelastic case, you can make a parallel and redo this for all the other cases. And the same kind of things are going to happen, the stability and conditional stability or not. All this can be extended to this new case. Okay. Okay, so just before that, so from here we can rewrite our constitutive equations. This is the point of this. Okay, so I can write this is a sort of universal. Okay, so the stress is the variation of the free energy with respect to the strain. Sort of a definition of what the free energy should be, but okay, so if I do this, I check, and I find that, okay, I got the elastic part. Coming from here, and then I have here, let me write it in this way. Okay. We're going to see in a minute that it's same as what we had before. Okay. So the other interesting part in this case is that we can write that there is a. Okay, so this one we're going to write in this way. We can write. Okay, actually technically it's this, but okay, it doesn't really matter. Okay. So the pore pressure is going to be linked to the variation of the free energy with respect to the variation of porosity. If I do that, I find that this is okay. Which is the equations we had before, but okay, written in terms of pressure as function of phi, not phi as function of pressure. Okay, and this also means that this quantity okay. So I have this is, I had written it indirectly in terms of stress, equal to elastic part minus P times V. That's what I had before. Okay. So we recover the same thing. And here we can write, sorry, there is a double half here. Okay. And this I can write simply. Okay. We can look at a few things which could be interesting. Okay, so, and of course, okay, we can, I'm not going to do this now, but we could define a phi star being quadratic function of J, and define the relation the other way. We can also introduce a W star, maybe if you want to call it like this way, could be a function of, well, there are many variants. We can make one which is function of strain and pressure, pore pressure. We could make one which is function of stress and pore pressure. And we can even make one which would be function of stress and phi. Okay, with the duality of the relations, but okay. Let's keep it this way for the moment. One thing which is still interesting to do, I guess I can remove this too. 6. So, if we look at the energy, okay, if I develop a little bit the things, I can write it. Okay. I can also write it this way, okay. Okay, if I develop this term here, I may want to regroup this one and this one. Okay. So this, I get something like this, and then okay, I've got this coupling term. And I've got the okay. So the interesting thing to look at in here is that this defines two elasticity tensors. Okay. Okay, you have H here, okay, and you have this thing. Okay. So, and we can see it is, could see it here as well. Okay. I could rewrite this here if I put things in epsilon together. Okay. I can also write sigma so this quantity, okay, so this is the same as this one. What does it represent? It's the elasticity, so it's the change of stress with respect to strain, with respect to change of strain, if I keep the porosity constant. Okay. So this is call it this way if you want. So in this case, for example, imagine that the pores are not connected. Okay. And I assume that my fluid was incompressible. Okay. So if maybe it's easier to imagine in terms of compression, but I'm trying to compress because the fluid is incompressible and the pores are not connected, the pore volume cannot change. Okay. So this is a limit. It's the limit where there would be no change in the. This one way to imagine the case where there will be no pore volume change. Again, in the linearized case, because porosity is not changing, but the total volume is changing a little bit. But again, I am taking my porosity with respect to the initial volume. So the volume of the pores does not change, so I consider that the porosity does not change. So the first order, okay? So in this case, this is the stiffness of the material, okay? While this one, you can, if you look at this one here, okay, what is this? This term. I could have written it this way, okay? I use the definition of pressure, okay? So I don't want to make it, okay, no, technically this is the function of phi, but this represents the pressure squared. Okay, so now if I strain my material point, my RV, keeping the pressure constant, that is exactly the opposite case, where the pores are connected and everything is plunged into a bath which is at a given pressure. Okay? So the pressure of the fluid in the pores cannot change, because the fluid can go out or in, just to maintain the pressure at the equilibrium level which is outside. Okay, and then this is the stiffness of my porous material. Okay, and we see that. Okay, these are tensors, but you can understand this as being the H is lower than H phi, or H is higher, stiffer than H. So it's stiffer in the case where the pores are blocked. In the case where the fluid can move, which makes sense. Okay, as I was saying before, I mean, if you're in this situation where you block the porosity, this really corresponds to the case where you have pores filled with incompressible fluid and the fluid cannot change, cannot move out. Okay, and so when you try to compress your porous material, they act like rigid inclusions. It's like if you put beads of very hard steel in the material, so it is going to reinforce the material. Okay, increase its elasticity. Okay. So this is one way to explain the. So you have to pay attention when you measure the elasticity of your material, in which situations you are. I mean, are you sure that you are in a situation where where we talk about the drain situation, you can take, the fluid can go out, or the completely undrained situation where you block the fluid flow outside. Okay, so this would be the case what I was telling you before. If you put your sample in a membrane, or like you do which prevents any fluid to go out. If you try to compress, then the fluid cannot go out, so it will stay there, and since it's incompressible, it will prevent any change in the porosity, the volume of the pores to change. Okay, so we are going to be closer to that. So what we measure is this. So you have to pay attention to what you measure, which situation you are when you measure the elastic coefficient, because if you want to do your test, I mean, are you in this situation or in this situation? You don't measure the same thing. And if you measure the two, this gives you an idea of the stuff. So unfortunately, it doesn't give you the single N or single B, but it gives you an idea of the BO quantities. And of course, you need to do another test. Maybe, for example, try to constant strains, constant pressure, strain the material, and see how the pores change, and this will give you the B. You can connect the change of porosity to the applied total strain. This is connected by the B. Okay. But this would be for experiments. We don't experimental case, but you have to remember that there are these two elasticities, and it's just the same as again in the thermoelastic case. Remember with the isothermal elasticity modulus, the one that is usually used, but you also have the adiabatic elasticity modulus, okay, which is used in the adiabatic staggered scheme. Well, this one. So the adiabatic is, in this case, is like keeping phi constant. Because if you keep phi constant, the pressure, of course, increases in the pores. It's like the temperature increase in the adiabatic case. Okay? So it's the equivalent of the adiabatic case and the equivalent of the isothermal case.
keeping the porosity constant is related to the area.
Porosity is like the entropy.
Okay.
So when we say adiabatic, it's actually isentropic in the thermoelastic case. Because there is no dissipation, so adiabatic is similar to conservation of entropy. So here, entropy, the equivalent of entropy formally is the porosity.
So keeping that.
The
constant.
equivalent of the temperature is the pressure. Okay. So temperature is like a force in that sense, and entropy is like strain. It's also a notion of what is intensive and what is extensive, for example. Okay. Temperature is intensive, pressure is intensive, while strain or porosity or entropy is something that you can accumulate, you can integrate and make averages. Same way as the porosity. Okay. Clear? And okay, the objective here, from in the context of this course, okay, because this is not again, I'm not supposed to do a course on polar elasticity itself, but this is just one other case which is for exactly the same structure, same framework as what we've seen before. Just thermoelasticity, diffusion, elasticity, porous. So Fourier, Fick, or Darcy is the same thing mathematically. Okay? It's really, you can make the connections between the. So you can. The experience you have now in doing thermoelasticity in terms of numerically solving a problem, you can extend it also to this case. This is the idea. Okay. All right. So we can try to push this analogy a bit further. Okay. So now we want to solve this coupled problem. So we need to solve typically this equation with these constitutive relations. Okay. So what do we know about this? Okay. You can guess that they would have the same properties as what we have seen before, but can we make sure that we do this? So this is an exercise if you want. Can we check the stability of the problem, the well-posedness of the problem? Okay. Can we demonstrate? So I'll let you say it, not me. So what do we need to check to demonstrate the well-posedness of the problem? The well-posedness of the problem so that the equations will behave nicely.
To start with.
The stability, yes. So how do we check the stability, or what is one way to verify the stability? Yes, to check the contractility. So can we find a norm which is never increasing? So a norm of the current state of the material, okay? So, again, you can do this in different ways, but okay, let me, okay, so make room, so let's see where is everything. Okay. So we have a domain, okay, and our unknowns are the displacement field. And okay, so now here we need to write things. So we can work either in terms of porosity or just to help here. So this is the actually we could formulate the problem in terms of porosity or pressure as a main. Of course, we have a relation between the two, okay, through the strain, but there's a question of how I define the state of my porous medium. Okay. So just for this, let's say we need to work with this. Okay. So why do I choose to do this? It's just because if I want to do a simple analogy with what I've done before, I can guess that this is the best way. There is a way to do it with the other one too, but okay, so here, why do I do this? Remember what I just said, that pressure is like temperature, okay? So if I want to make the analogy with the thermomechanical case, the thermoelastic case, it will be easier to start from there, okay? Okay, so remember we want to have a so we want to do this. So any suggestion? I want to let you brainstorm a little bit. So if you go back, would you be okay? To reassure you, I'm not going to ask you in the exam to come up with a norm. Okay, it's a bit too much. But here we are in the course, so a bit more time. You have your notes and everything. So, can you, by analogy, can you propose a norm which we could try to see if it works based on what we have done before?
Can we raise the free energy and the pressure?
Yeah. So yeah, this is exactly this. Yeah. So if I write, I've got my 1/2 is here. Okay. So now this is a norm of the whole domain. Okay. Okay, and if I write something by analogy to what was working with thermoelasticity, okay, where epsilon is the gradient of U, okay, or the symmetric part. Sorry, this way. And would this work? It should, because by analogy it should. No, we need to check it. Okay. So let's go through the derivation again. It's something which is it's a good refresher. Okay, but so what I want to check now. So again, I've got. Okay, and I've got, here is static, so I don't need velocities, okay? And I've got, initial conditions, okay? And this gives me, this generates from this initial condition I have something solution, okay, which is controlled by my equations, which I will rewrite afterwards, okay, as we need when we will need them. And I've got an alternative, another situation. I've got actually I should have written this in the other way, but okay, doesn't matter. Okay, remember what I consider, I got two situations with different initial conditions. Okay, and I know I want to compute the evolution of the norm, here the square for convenience, of the distance measured by this norm between the two solutions, okay? So this so, and okay, and this is this integral, okay? So I need to take the time derivative into this, okay? Can you guide me to see, what should I write then? Okay, what is, okay, so again, I'm going to use small strength, so this is consider the domain does not change. I'm doing the integral on the initial configuration if you want.
Is there such a thing as epsilon tilde?
What?
Is there such a thing as epsilon tilde?
Yes, of course, yes.
Okay.
Yes, because, okay, this, we
So
have
it's
epsilon
Minus epsilon.
is the, then I've got an epsilon tilde.
Mm-hmm. Tilde. Okay.
Okay, this would be the symmetric part, okay.
Can you do the same for H or?
No, H is a constant.
No, H is constant, so.
H is the rest symmetry. I mean, there's the same material in both cases, just the initial conditions which change. So H is the same, A is the same.
So is it epsilon minus epsilon tilde?
So we have, yeah, so everything is squared, so when we do time derivative, it will be a 2, you just need to kill the 1/2, okay? And here we can write it indeed in this way.
H. And then epsilon minus epsilon tilde again. Plus P.
Okay, so again, I could write it the other way if you want, but H is symmetry is the same. And this one is
Minus P
P.
tilde.
P minus P tilde. P dot.
Second constant.
Okay. what do I do next?
You can rewrite.
So we need, okay, now we're going to have to use the different equations we have. Okay. So here, okay. Let's look at this one, okay? I want to guide you. So we wrote we have, you know, that P is equal to N. Right, it's minus. Okay. P is given by this, right? So, and the same thing for P tilde, of course. Okay, and P tilde. Write this too. Okay. But okay, I'm not so much interested into this than the P dot. The P dot is simply okay. All right. Now, so can write P dots. Okay. Now let's put this in here. Okay, so let's do it quietly, but so let me just look at this first. So here I've got terms in epsilon dot minus epsilon tilde dot. And I'm going to put this in here. There will also be a term in epsilon dot minus epsilon tilde dot. Okay? So let's try to put them together. Okay? So here I've got this, I can write it if you want this way. So this itself, this whole thing will be contracted with epsilon dot, so I could have put it there, but put it on the other side for convenience. But okay, and then from here I've got my so if you want, maybe the easiest way is to do this. And directly replace this, okay? So I've got the P minus P tilde times minus B epsilon dot minus epsilon tilde dot, okay? So here I've got minus P minus tilde B, and the whole thing I'll contract it. Okay, and then I'm left with the other part, which is I've got here P minus P tilde times phi dot minus phi tilde dot. Now, if you go back in your notes a few lines above, how can we write this? This looks very much like something we. You can just check your notes if you want. What does this look like?
It's like the pressure, like, not pressure, velocity.
No, H epsilon is
Oh,
stress. So we had the okay again the do this here. Okay, that's what we had. Okay, and same thing for the tilde quantities. So this means that this is we have H epsilon minus PB is sigma, and we have an H epsilon tilde minus P tilde B sigma tilde. Okay, so this is the stress in one case and the other one. Okay. All right, so let's continue. We're not that far from the end, actually. So let me hold this. So. Okay, so what's next? Now we need to use the conservation equations. We'll not use them. So here, note, we have used this constitutive equation. We have used this constitutive equation. Okay, so we have used these two already. So what's left? We have all the conservation equations. Balance equations, and we have the Darcy equation. So which one should we use now? Okay, so there is a small manipulation to do, which is a very classical one. You see sigma contracted on epsilon or epsilon dot. This calls for something. It's always the same thing. maybe let me ask the question in another way. What do you know about sigma and sigma tilde? Yes, good. Not velocity, sigma. What do you know about sigma? Sigma appears where in the... So we have already used this one. Sigma appears somewhere else in the list of equations we have.
Balance equation.
Balance equation, yes. Balance equation is okay. So you would like to see a divergence of sigma somewhere. How do we get a divergence of sigma? No. Remember, this is gradient of velocities. So you have something times a gradient, and we'd like to transform the gradient into a divergence.
You can use green law.
Hmm?
Green law.
Yeah, the divergence theorem or the Green-Rossum-Razi theorem. Yeah. So let me rewrite it for a moment here, but okay, just quickly. So the epsilons is I'm going to actually this is, you can write it this way if you want. So it's u dot actually, okay? So it doesn't matter. I can write u dot. It's easier. So this I can write this first part. I can write it as okay, so the divergence theorem moves, it's an integration by part fundamentally, so move the derivative from here to here. It's a minus here. Okay, and for the moment, let's leave the other term as it is. One thing at a time. Okay. So what can I say about this and about well, this whole thing here?
Zero.
Yes. So this one is 0 because I got this. And the same thing with the tilde, but the f does not change. So the difference between the two is equal to 0. Okay. This whole term vanishes, okay? And this one, same thing. So you have two parts of the boundary. you have a part where you impose the displacement or the velocities. So this one is 0 there. And the part where you impose the traction vectors, and this part is 0 there. Okay, so it's either one of the two is 0. Okay, so this is also 0. Okay, I'm only left with this. Okay. So, okay, this is equal in the end to okay. There as well. Just want to use this here. So what do we know? How do we handle this thing? Well, no, not first. First, we need to do. So what do we have left? We have used the conservation of momentum or static balance equation. So we have conservation of mass and Darcy relation. Okay. So. We have this, okay? Now, remember, how do we connect? C is connected to phi, okay? So, for us, C dot is, since the fluid is incompressible, the change of concentration is just linked to the change of porosity, okay? Again, I assume that the pores are always fully filled with fluid, with incompressible fluid, okay? So it's a saturated case, okay? Okay, I got this, and I also know that J constable relation. Okay, so using this, I can write phi dot as a okay. Actually, I can also do the same thing for the other one. Yes. Okay. So this when I do the difference between the two, the R is going to vanish. Okay. So this is compressive. This is the density is uniform. I can put it there. And just check this. Actually, I can write it this way if you want. Okay. Actually, this so there is a dynamic and static viscosity. I never remember which one is which, but this is the other kind of viscosity. So I can call it eta f just so it doesn't matter. It's a positive number. Okay. So now here, if I replace, so I got this. What should I do with this?
Gain 0.
I can do the other way, okay? Whoops. Okay, let me write. Okay. Again, this quantity here. Okay. And again, the two possibilities. The boundary, either you impose the fluid pressure, the fluid velocities, or the fluid fluxes. So either one is going to be, either this or this is going to be 0, the boundary. So this whole term is actually equal to 0. Okay. And I'm left with this one. Okay. This is a square of something, so it's positive. And this also actually restricted after 0. Okay. So this product is non-positive. So my norm is decreasing. or it's non-increasing. So my problem is stable. And again, I've demonstrated my stability. And you can see that this is non-zero when this is non-zero. So the moment that there is this is linked to the dissipation, linked to the transport of the viscous fluid. Okay. There's a viscosity. I mean, this typically shows you that it's there. If there is no transport, there is no dissipation, it's zero, it's conservative, but the moment there is the transport, this dissipates energy, because physically you can think of it, I mean, in the small channels between the pores, there will be a boundary layer with viscous friction of the fluid on the sides of the channel, and this dissipates energy. Is the physics behind it, but okay. So we have a system of equations which has all the nice properties. Okay, and so we can do can apply everything we've seen before. So here, what I suggest we can do again as an exercise. It's a repetition. Okay, but I think it's good for you to repeat the procedure once more, see it as an exercise. You can try to think about it already, but next time on Wednesday what we can do is to derive, or we can look at the modality scheme if we want to start with, but what are the staggered scheme we can imagine for this. It's quite immediate because it's really apparent to the thermoelastic case or the diffusion mechanics. But again, doing it again is going to help you to understand that. Okay, so yeah, let's stop here for today. Okay, so there's a very strange program, I don't know why. So Wednesday we have 2 hours in the morning. There is 1 hour in the afternoon.
Huh?
So it's normal. So it's
This is what is, okay.
so you have to go 3 hours. That's it.
Yeah. So, okay, so we'll see how far we go, but I think we can do the 2 hours.
11 to 12.
Look at the staggered scheme, and we can leave the hour in the afternoon for questions and answers.
It's
You
one.
updated on.
Chris on a cracker.
You have to look at Moodle, yeah. You know you can synchronize the Moodle with your own calendar. Otherwise it made little sense to have 1 hour in the morning, 2 hours in the afternoon. That's why I had it changed. So it's 2 hours in the morning, 1 hour in the afternoon. No, but it's been updated. I asked it a while ago, but it always takes time to...
So
So
It's pretty
short
to
one
move.
is 2 in the morning, 1 in the afternoon.
Yes, and that's what we do. Actually, I have something to do at another meeting at 3 in the afternoon. Since I even think you have course in from 8 to 10 in the, no? Okay. All right, so I see you on Wednesday.
Monsieur, je peux vous parler un petit peu de petite transmission.
I have concrete until 6 today.
Je sais qu'il y a un mail qui est remis en France.
Oui, oui.
So when
Oui,
the
non, mais
fuck
ok,
am I
c'est
supposed to actually study for my
Il y
exams?
a un bug, je sais pas ce qui s'est passé. Donc,
I don't want to think about
je
that.
comprends qu'il
I'm
y ait
so
des
angry.
Non, non, mais là, on n'est pas... Il n'y a pas de...
I don't have
C'est pas...
a
C'est quoi, c'est 3 jours de...
I have an extra one.
presque
I
Noël.
have two
Oui,
computers.
bon, ça va faire un vrai,
Oh, they're all fine.
Est-ce que vous voulez que je vous renvoie
It's more kind of
les gens à
similar.
l'écrit parce que je ne l'ai pas encore envoyé, l'idée, comme une reversion de départ. Vous avez en fait la conclusion, mais sous forme de capture d'écran. Ça va pas être très précis.
Oui, je préfère l'avoir...
à l'écrit de ça.
Ouais.
Je vous renvoie un mail aujourd'hui. Merci.
Do you remember what you mentioned about the software with trouble from that time?
I looked at it a little bit yesterday.
Do we have to get that during the exam? Because he said something about like he gonna put one or two questions.
If you ask, Professor,
Yes.
please don't erase that, talking about, on,